Okay, so what we'll be studying today is this grand canonical ensemble. Excuse my voice. So here we have initially studied about a microcanonical and canonical ensemble. So in microcanonical, we know that the temperature remains, uh, the energy remains constant because it's a closed system. And then in canonical ensemble, we know that there can be exchange of energy, but then the temperature remains constant. What happens now if we have a open system and there we have this grand canonical ensemble? So we will try to see how we can use similar concepts to derive the partition function for grand canonical ensemble and how that can be used to derive the different thermodynamic parameters. And after that, I'll spend some time talking about Ising model. Okay. So, so this is the basic outline as it goes in all sessions. I'll first talk about the basic concepts and I'll discuss certain problems. You can tell me if you have some doubts. Okay. So, macrocanonical ensemble. So microcanonical energy is constant, it's a closed system. Canonical ensemble energy exchange is allowed and their temperature is constant. Now if we have an open system, what happens? So there one can exchange particles as well as energy. Then what happens is we have this macrocanonical ensemble, which is so a macrocanonical ensemble is described by the parameters temperature, volume, and the chemical potential. Now it's not the number of particles anymore because now the number of particles can change depending on the interaction with the surrounding. So how do we go about solving such ensemble? So it's similar to what we do for canonical. So initially for canonical we had a heat bath and then we could exchange energy with the reservoir. Here it's a heat bath as so it should be heat. So it's a heat bath as well as it is a particle reservoir. So you can exchange both energy as well as number of particles. We consider that the total system, including the reservoir and the system, like the total uh, system is a microcanonical ensemble. Then the energy Es, which is the energy of the system, Er is the energy of the reservoir. So Er plus Es is the total energy which is conserved, which remains constant. And similarly, the number of particles, Ns, number of particles in the system, Nr, number of particles in the reservoir. So the sum of that also remains constant. So what we can then do is, so if we consider that the reservoir is very large, then we can do this approximation. So what this tells us now is that the probability of finding the system with a particular energy Es and Ns is same as finding the number of microstates for which the reservoir has an energy of E minus Ai and N minus Ns. So that is given by the number of microstates. It's proportional to the number of microstates. So now if we do an expansion, similar to what we have done for canonical ensemble, there we had done this for just energy. Now we are also doing it for the number of particles. And if we do that, we know from our thermodynamic relations as well that del S del E is 1 by T and del S del N is minus mu by T. So if we do that substitution here, we see that the number of microstates for a particular system with where the energy of the reservoir is E minus Ei and the number of particles in the reservoir is N minus Ns is given by this expression here. Okay. So in canonical, we just had e to the power minus Ei by kt. Here we have this additional plus mu ns by kt term, which comes because now we can exchange particles. Is this clear till here?
Yes, ma'am.
Okay. So then what we do is, now this is proportional. So if we use the normalization relation for probability densities, we get this expression for the probability density. So the denominator here is actually the partition function for the macro canonical ensemble or grand canonical ensemble. So now if we do so this is for a discrete system where the energy levels are discrete. If we have a continuous system, we have an expression like this. So this denominator is called the partition function. Now what happens if I have to find the average energy, U? So what we are doing here is that if you remember from the last class, whenever we do average energy, we are actually multiplying the energy of each state with the probability of being in that state. Okay. And similarly, it goes for the average particle number. So this concept is clear, right? Like last class I had discussed why. So whenever there is something averaging that we are doing, we have to multiply that quantity with the probability of the each value in the sample space. Is this clear? Hello.
Yes.
Yeah. So now this is the expression for U, and this is the expression for the average particle number, and this is the expression for the macro canonical partition function. So here you have this additional alpha n term. Well, alpha is mu by kt. So can you tell me, is this expression for the distinguishable or for indistinguishable particles? What is this partition function for?
This is for, I think, indistinguishable.
This is for indistinguishable particles. Is that correct?
Yes.
Why do you say so?
Because 1 upon h to the power 3 and factor is coming.
No, 1 upon h to the power 3n comes from the uncertainty relation that each
Oh, oh.
has a volume of h to the power 3n. So that has a different origin. So this is a complete different concept. See, so we know that dp dq is always like greater than equal to h. Now you have in 3D, it will be for each microstate d3q d3p for each particle. So then it is h cube. And then if you have n particles, it will be d3np d3nq. So the minimum volume in the phase space will be h to the power 3n. So that is a complete different concept where we bring in the uncertainty that lies in like the Heisenberg uncertainty. But this is a different question. This is the question of the Gibbs factor. So, um, so let me repeat what I had said initially. So, if you have n number of distinguishable particles, that means you can arrange them in n factorial ways. Okay, but if they are indistinguishable, that means you cannot just look at them and distinguish. That means just placing it in different positions won't make any difference. So there the number of microstates get reduced. Is that concept clear? So it's like, suppose if you have three numbers, 1, 2 and 3. Okay. So how many ways can you write it? You can write it as 1 2 3, 1 3 2, 2 1 3, 2 3 2, 2 3 1, 3 1 2, 3 2 1. So that is 6 ways. But now consider you have this kind of sorry, so some structure, okay, some structure, and you have three of them. So here obviously they are distinguishable, but that is mistake in the drawing. But consider that you have three similar objects. Now just placing one here or interchanging won't make any difference. So that means whether you place this at first or you place this here won't change anything. that is the same state. So that means in those cases you have to divide the so the microstate number decreases, and then you have to divide it by n factorial. So in this case you have to divide it by 6. It is 3 factorial. So this tells us that if we have a
Actually, uh, I am pointing something because is this expression for distinguishable particle because the Hamiltonian is classical.
the Hamiltonian
And
is
in the
I thought
expression of e to the power minus beta h cube Hamiltonian. जो अच्छा.
Hamilton is not specified here. It can be
Okay.
we don't have the Hamilton specified yet. It's a general formula. Think think logically. Your Hamilton is not being given yet. It's just just the general derivation of grand canonical ensemble partition function that we are doing. So then depending on whatever system you have, you will change the h. But that's not the question. The question is that here first you were talking about h to the power 3, and is that concept clear? That comes from Heisenberg uncertainty. Is that thing clear first?
Yes.
That has nothing to do with distinguishable or indistinguishable, okay? But then what happens when you have distinguishable or indistinguishable particles is the number of microstate changes. You understand what I was describing here, right? If you have three different numbers, so 1, 2 and 3, they are distinguishable. You know this is 1, this is 2, this is 3. Then you can rearrange them in 3 factorial ways, and all of them will be different state. But if you have 3 identical objects, just placing them in different places won't make any change. Okay, you can just have one state, that is this. Whether now if you bring this here, if they are similar, that won't change anything. So that means your number of microstates is getting reduced. So in that case, that means if you have indistinguishable particles, you have to divide by 1 by n factorial. In this case, you don't have 1 by n factorial term here. That means this is for distinguishable particles. So this 1 by n factorial is called the Gibbs factor. That comes in when you have indistinguishable particles where the number of microstates has to be reduced. Is that clear?
Yes.
If you have doubt, just ask me, because this is like I have been repeating this for quite some time. So if there is still some doubt, just ask me, because these are very fundamental concepts. Okay. Okay. So this is for distinguishable particles. We don't have the Gibbs factor. Okay. Now, how do you get to the entropy if you have the phase space density? We know that this is the relation, and that holds true for all ensembles. So because now we have already got the expression for the grand canonical ensembles phase density, probability density, we'll try to find the entropy. And if we put that expression here, this is what we get. So if we now look at each of the terms individually, this k ln z, k beta h into this integral, inside this integral, and then this term. Okay, so what we do is we compare with our definition for average energy, and you see that this is the expression for average energy. Okay, and this is the expression for average number of particles. So if you now compare this with the expression that you have here, what you will find is S can be written by something like this: k ln z plus k beta into this average energy minus k alpha into average number of particles. Is it clear how we can write from here to here? So here alpha is mu by kt and beta is 1 by kt. Is this clear how we are getting from this step to this thing here? Hello? So,
Can you say, ma'am, again in this derivation?
so this is clear, right? You have just put the expression for rho here, okay? This is the expression for rho.
Rho is probability density now,
Rho is probability density. So when
and
you do the averaging of any quantity, you have to do an integration of that quantity multiplied by the probability density. So here this is your probability density, and then you multiply by k, l and rho. Now in the expression for rho here, you again put these values. Is that clear? So this is your expression for this is your expression for rho. Okay. Now what you do is you do an averaging of k, l, l and rho. So first you write k, l and rho, and then you multiply by the phase space density. That gives, and then you integrate. That gives you the average value of this quantity minus k, l and rho. Okay. So here you have just put the, so after ln whatever you have put, so this thing inside the bracket is actually k, l and rho, and then you have multiplied by rho of grand canonical, and you have done this integration. So that gives you the average value of minus k, l and rho, and that's the definition for entropy. What you then do is, so if you just look at the integration of this term, this second term, so you see that you have k beta, and then you have to do this integration over h. That means you are actually finding the average energy. And the second term, if you take k alpha out, you are doing the integration over n of n over this over the entire phase space volume. That means you are finding the average number of particles, because these are the expressions for average energy and average number of particles. So if you use this relations, so if you expand this and then if you use these relations, what you get is this expression for S. Is that clear? Now is it clear?
yes.
So here alpha is this term, beta is 1 by kt. It's just the definition of average energy and average number of particles that we're using in this relation. From this relation, we put that value here and we get this expression. Okay. Now what's that means, you can write this as something like this. So average energy can be written as U, and then you can write beta as 1 by kt, you can write alpha as mu by kt. Okay, then you can take t on the other side and you get to this expression. So u minus ts minus mu n is equal to minus kt ln z. Okay, so if you remember, this kt ln z has a similar kind of form to what we initially had for free energy. So what you can do is you can define this as a potential. Okay, so you can say that is phi, which this is a potential that defines the macrocanonical ensemble, and that can be evaluated from the partition function by this relation. Okay, so initially for canonical you had an expression like F is equal to minus KT ln Z, where F was your free energy. Here you have a similar potential, and that is written as minus KT ln Z. That means from phi you can find the different thermodynamic variables. Okay, so if you write and is just rearranging this statement and using the expression for u, you'll see that PV by KT is equal to ln Z. So this is something which you can which you'll see that later using this relation, we can derive different kinds of thermodynamic variables. We can also do that directly from here. Okay, so now this is your expression for the partition function. Okay, so how we can write this is now is that we can take these two terms separately. So integration of this term d3np, d3nq, e to the power minus beta h is actually the canonical partition function. Okay, and then we have this added term of e to the power mu by kt into n. So that is something which we can write in this way. Now this, you'll see how we can write this canonical partition function for n particles in terms of canonical partition function for one particle. Okay, so here first of all this factor e to the power mu by kt is called fugacity. Okay, so it's the weighted sum of all canonical partition functions. So this is for each value of n. So initially if it was a canonical ensemble, you would have just gotten, you have just got this. Now what happens is your n can vary from 0 to infinity. So for each value of n, each ensemble with some value of n, you have a weighted like a weighting factor here, and this is called the fugacity. Okay, so what you then do is for indistinguishable non-interacting particles, you can write the partition function for n particles. This is the canonical partition function. So you can write it in terms of partition function for one particle by this relation. And then if you put that in this expression here, you'll get something like this. Okay. So if you look closely, the expression that we get here is an expansion of e to the power x, where x is this parameter here. Okay. So in e to the power x can be written as summation n equal to 0 to infinity x to the power n by n factorial, right? So that means this summation can be written as exponential of this entire thing that we have in this within the brackets. Okay, so then that means if we find the canonical partition function for one particle, you can use this relation to get to the canonical partition function. You can get to the partition function for a macro canonical ensemble which is specified by t, v, and mu. Is this clear till here? Is this clear till here? Hello?
Yes, ma'am.
Okay. So that means whatever we had done in the last class to in order to solve for different systems and finding the partition function, if we can find the canonical partition function, we can actually find the partition function for macrocanonical ensemble as well. Okay, just by using this relation. So if you have ideal gas, if you remember, this is how we had found the canonical partition function. Okay, we had used the substitution, and finally we have got to this expression. So this is the canonical partition function for n ideal gas molecules. So what will be the expression for one ideal gas molecule? It will be just v by lambda cube, right? So now if you know the canonical partition function for one particle, you can use this relation, the one that we were, so use this relation to get to the grand canonical partition function. And this is what we get. So here you have put the expression for the canonical partition function for one particle. Okay. So once you get to this expression, you can use this to find the macrocanonical potential. Okay, and from there, using this relation, this will tell you the del phi del t at constant entropy, constant volume, and mu is given as minus of entropy. So similarly, pressure and number of particles. So that means if you can find phi, which you can get from the partition function, you can find the different thermodynamic parameters. Okay, so that summarizes in a way the different ensembles and their partition functions. So you can see that initially we had seen that if G is the number of microstates, we can find entropy by using the relation KLNG. If we consider a canonical ensemble, and if we know the canonical partition function, we can use this relation of minus KT ln Z to find the free energy, the Helmholtz free energy. Okay. And in the grand canonical system, if we know the macrocanonical partition function, you can again use this relation to find the macrocanonical potential. Okay. So now what we have to look into is the fluctuations in macrocanonical ensemble. So here these things are very important in order to understand under what conditions will the fluctuations be less from the mean value, or how does it depend on the number of particles, things like that. And if you look at your assignment questions also, you'll find questions with this kind of concepts. Okay, so this is your grand canonical partition function. Okay, now this is your expression for the mean particle number. Can you tell me how we can write the mean particle number in terms of the macrocanonical partition function, just looking at these two expressions? Look at these two expressions and tell me, have Z find an average. Any idea?
Ma'am, are you speaking? Your voice is not audible.
Yeah, no, I'm not speaking. I was giving you some time to think. Now you can hear me, right?
Yes, ma'am.
Huh. I was giving you some time to think that if you have Z, how do you get to N? So look at this
Uh,
formula here.
One Z summation from summation of I and N of N times Z.
And N times Z, is that correct? See, Z already has the summation in it, right? You cannot replace this term by Z, and you cannot take N out because you have N here and here as well, and it's a summation over N. So think that you have this expression. This is your Z, okay? Now you have to do something so that you can get a N out here. So what will give you an N out here? Looking at the expression for Z. So when you do differentiation of AX with respect to X, you get a out, right? Look at this expression here and see what is what is different from this expression and this expression. The first thing that you notice is you have a N out here, okay? And then there is 1 by Z. So in order to get a N out here, you have to do an differentiation with respect to mu, right? if you do a differentiation with respect to mu, you'll get a n out. Is that correct? Am I making sense?
Yes. Yes.
Yeah.
But ma'am, the term still has got a N in it, right?
Yes. So this is your expression for z. So now if you do del z del mu, what will you get? You'll get this minus n out, right? Minus n out into this expression, but you'll get this minus n out, right?
Ah, okay, understood. Yes.
Right. So what this tells us is that you have to do a differentiation with respect to mu. But there's another thing. There is a 1 by z factor here. Now you know that differentiation of ln x is 1 by x, right? So that means what you have to do is actually a derivative with respect to mu of kt ln z. This is your z. Write the expression for kt ln z and do a differentiation with respect to mu. Do you get this expression? Check. Check if you get this expression. This is very fundamental. Whenever you are given the partition function, you have to find the average energy or the average number of particles. You have to use this concept. So see if you use this relation, do you get to this thing or not?
Yes, ma'am.
Anushka, is it clear?
Yes, ma'am.
Okay. So that means now this KTLNZ can be written as minus of phi, which is your grand canonical potential. Okay. So that means if you know the partition function, you can write KTLNZ and then you can do a differentiation with respect to mu to get n. That is the average number of particles. But what we want to finally get to is the fluctuations. So that means what we want to see is we want to see the deviations from the mean value, and that is given by the standard deviation. Okay, and how is standard deviation defined? It's defined by the expression given here. So you have to find the average of n square, and you already got the expression for the average n. Do a square of it and do this difference. That will give you the variance, and root over of that will give you the standard deviation. So how do you find n square? So n square is n square average, right? So whenever you're doing the average, you're multiplying by the probability of that term, of that quantity. So if you do that, this is the expression that you get. Okay. And then now you have 1 by z, you have n square. That means you have to do a derivative with respect to mu twice. And because there's a, so you have 1 by z already here. And then if you do a derivative with respect, like if you do a derivative twice, what do you get? You get this expression, right? So this n square, like summation of n square e to the power minus beta ei minus mu n, can be written as this term here. It's clear, right? This expression.
Yes, ma'am.
Yeah. So now what happens is you can write, you know from the initial definition of average n that kt del z del mu is given by z into n. You're just multiplying z here. So z into n average is given by del u of so, so kt ln z derivative will be 1 by z del u. So that means KT del Z del U is equal to Z into average N. Okay. So now if you use that relation in the expression for N square, you get an expression like this. And then what you do is you do the, so it's the product rule. Del del U of xy is, so you do a derivative of Z, keeping n, considering n average as constant, and then you do a derivative of this term keeping Z constant. So you get to this expression of n square. So the first term is the square of the average number of particles. That means now you have got an expression for the variance, okay, in terms of the derivative of the average number of particles. This average number of particles can be considered as the thermodynamic particle number n, which we consider like whatever we consider as n for microcanonical ensemble. So that is what is the average or the mean value. So so you can replace this here, and that gives you the expression for the variance. Okay, clear till here?
Yes, ma'am.
Yes, ma'am.
Right. So now what's interesting is that we'll see that there is a relation called Gibbs-Duhem relation, which relates the different intensive variables with the conjugate extensive variables. Okay, and this is the relation. What this tells us for our system is that if mu is the chemical potential, you can write d mu by this expression here. Here small v and small s are given as v by n and s by n. Okay, so that means this can lead to this expression here. We will see why this is useful, because using this we will write the variance in terms of some known, so in terms of measurable quantities. Okay, so we'll see how we get there. So from here we can write this expression. Okay, so what now we have to use is that consider that pressure is a function of T, V and N. Because pressure is an intensive quantity, that means that it will be a function of V and N only by the intensive combination of V by N. So that when you change V, so when you change V alone, N should also change, and V by N is the only way in which pressure should depend on these parameters, because otherwise they'll be extensive, but pressure is an intensive quantity. If you just change volume or just change the number of particles, pressure is not supposed to change. Okay, so that means pressure is a function of V and N only in the form of being a function of V by N. Okay, so now if we use that relation, that means pressure is a function of T and a function of V by N. So you can write dP dN by this relation here, where actually you're keeping the volume constant and you are just looking at the variation in N, okay, and how that changes the pressure. So it's like your the parameter on which P depends is V by N, and then the volume also changes with N. So you have an expression like this. Okay, but then now if you consider that the pressure is like it's the volume that is changing, that means it has to change something like this, where it changes, where the pressure changes only by like has only dependence on the term of V by N, but then V in V by N, when we change volume, the N also changes. Okay, so that means this is the expression for del P del N, and this is the expression for del P del V, right? So if you now compare these two, you get this expression. Now initially from the Gibbs-Duhem relation, we had got to this expression here. Using this two, what we get is a relation like this. Now if you remember in the expression for your variance, you had a term of del N del U. So now if you substitute, you get this expression. Here sigma n is your standard deviation, n is the average number of particles, and now you have written it in terms of the temperature, the volume and the compressibility, right? So because compressibility is an intensive quantity, temperature is an intensive quantity, that means your fluctuation, which is defined by the ratio of standard deviation to the mean number of particles, goes as 1 by root V. And this is of fundamental importance because now this tells you that because V is an extensive quantity, that means this fluctuation goes as 1 by root N. So if you now increase your number of particles, so as N increases, your deviation from the mean value will reduce. Okay, so if you have U, like if N tends to infinity, it will go close to the mean value, and that means in those limits you all this macrocanonical ensemble will also behave like a canonical ensemble, and that will also match with what you get for a microcanonical one. So all the variations about the mean will reduce if as you increase the number of particles. Is this clear till here? Okay, so now that was the fluctuations in number of particles. If you do the fluctuations in energy, what you have to do, you have to do something like this. So this time you are doing a derivative with respect to beta. Okay, because see, you have this EI term here. That means what you have to do is you have to do a differentiation with respect to beta, only then EI will come out, right? So, so this is your expression for the average energy. Okay. Now, similarly, you can get an expression for E square, and you can find the standard expression for the standard deviation or the variance. Okay. So, I'm not going through the derivation in details, but what would be interesting is that if you do some changes here, so you can see that it's constant with respect to z, where z is your fugacity, but you have to change this in terms of constant n, do some chain rule and some substitutions, so you get to this expression. What is this telling you is that the fluctuation in energy in macrocanonical case is always larger than the canonical case. Okay, this is your fluctuation for the canonical case, and you have some additional term. So for macrocanonical, it's always larger than canonical. And what's again interesting is that all ensembles with large particle number yield same results, because in all these cases it will go as 1 by root n. Okay, so if you increase n, the fluctuations will reduce, and then all of these ensembles will give you same results. Okay, now let us, so with all that knowledge that we have had, we'll have a quick recap of some concepts. Okay, so which expression here shows the average energy within the canonical ensemble? What will be your answer? Can someone tell me what will be the answer here?
It's
Hmm?
C.
C. Everybody agrees, right?
Yes,
So
ma'am.
here, this e to the power minus beta ei by z is actually the probability of being in the state with energy ei. So whatever average, whatever like averaging you are doing of whatever parameter, you have to multiply by the probability of being in that value. Okay, now consider that you have three collections of particles. Okay, and then three different kinds of ensembles: microcanonical, canonical, and grand canonical. Which one physical property is constant in all these three ensembles?
Volume.
Is it volume? See, volume is an extensive quantity. So that means if you change the number of particles, your volume is supposed to change.
Uh, uh, Pressure. No, no. It's total number of particle
So
because
what happens when you have a grand canonical ensemble? Whatever we are discussing till now was a grand canonical ensemble. And how was it different from a canonical one? So you can, that it was an open
Because
system.
like
That would be temperature because if we change the number of particles, the pressure and volume will change, but temperature will not depend on uh,
but
that.
canonical ensemble just we use the heat reservoir for changing the temperature.
Canonical ensemble.
In canonical ensemble we use heat bath, na?
In canonical ensemble, you use a heat bath, right? Right.
So how the temperature will be constant?
So when you use a heat bath, what happens is you can exchange energy. How do you define a canonical ensemble? You define it by the parameters of temperature, volume, and the number of particles. So it's a system where you can exchange energy, but it's in equilibrium, thermal equilibrium with the reservoir. So the temperature is constant there, right? You understand, Abhinav? When you
Yes, yes.
describe in microcanonical ensemble, the energy remains conserved, constant. In canonical, your energy can change, but your number of particles and temperature remains constant. In grand canonical, your temperature remains constant, your chemical potential is defined, but the number of particles and the energy can change, right? So that
Uh,
means, tell me.
in grand canonical ensemble, man, just a total number of particle will be changed.
It will
Uh,
change, right? So when we had done the initial definition, if you look at 1 second, wait. If you look at the initial first definition that we were doing, what is this telling you is that your number of particles in the system can change because it's an open system. You can exchange particles with the reservoir. But what we were doing is we were considering this total thing as a microcanonical ensemble. Total meaning system plus reservoir. So Ns plus Nr, which is like here Nr, that remains constant. Okay. But when you define the system, the system can always exchange energy. So the number of particles in the system do not remain constant. Is that clear?
yes.
That means if I go to the question, so it should not be the number of particles because the number of particles do change in the grand canonical. It should not be the volume, right? Because volume is an extensive quantity. If you change the number of particles, the volume will change accordingly. Correct?
Okay, so the only pressure is, I think, will constant.
But temperature can also be, right?
Temperature. I think I have actually I have problem with pressure and volume. If pressure will be changed, then the volume also change.
So if number of particles change, then the volume do change. But pressure is
Yes.
an intensive quantity, so V by N remains fixed. Pressure
Hmm.
is a function of V by N, right?
Yes, yes. Yeah.
So pressure should not change just by changing the number of particles, or so, because when you change the number of particles, accordingly your volume will adjust, and then V by N, if it is constant, then pressure is an intensive quantity. Considering it to be an intensive quantity, it should not change. But what would remain constant is the temperature, right? Because temperature So if it is a microcanonical ensemble, that means it's a closed system. So there is no exchange. Then if you have a canonical ensemble, there you can exchange energy, but your temperature remains constant. And even in the grand canonical case, your temperature is not changing. It's the energy exchange that's happening, right?
Okay. So the answer will be pressure.
The answer should be temperature, right? Because see, the temperature should be same in canonical or in grand canonical. Your temperature does not change, right? Because you're interchanging with the reservoir, but your T is fixed. You are defining the system by T, right? And microcanonical is a closed system, so there is no exchange.
Yeah. Okay, ma'am. Okay. Understand.
Anushka, you think it's temperature, right?
Yes, ma'am.
I think it too. See, this solution I did not find, but it's whatever our judgment tells, it should be temperature. Okay, so now consider the case of an ultra relativistic gas, okay? And we had already done the solution for the canonical ensemble, and we had got something like this, right? So this is your Hamilton, you put it in the expression for Z, you solve this integration. Here you take v to the power n out because your Hamilton only depends on p. Then you change to spherical polar coordinates because it depends on the magnitude of p. Okay, so integration of d3p is written as integration of 4 pi p squared dp. You do the substitution, use the gamma function, and this is the expression for the uh, canonical partition function for n particles, right? This much we had done in the last class. Now, how should we use this relation to get to the canonical ensemble for the macrocanonical one? What should we do? Any idea?
What is the question, ma'am?
The question is, this is your partition function, canonical partition function for n relativistic gas molecules, right? This we had done in the last class. Now,
Yes. Yes. Yes.
if you know this, how can you get to the macrocanonical partition function?
For macro canonical partition function,
From here.
temperature is constant.
So, what is the relation between canonical ensemble partition function and macrocanonical ensemble partition function? We just derived that some slides back, right? So, if you look at this expression here, this is your partition function for canonical ensemble with n number of particles. And this is your grand canonical or macrocanonical partition function. And this is how they are related. And what we saw is if you expand this thing further, considering that they are indistinguishable and non-interacting, we get an expression like this. We put this expression here and we get to this expression. So this is your macrocanonical partition function. This is your canonical partition function for one particle. Okay, and this is how they are related. Now in the present question, you know this thing, Z of TVN. You want to find this. So how will you do that? This is known to you. You want to find this. Look at this relations, this one, and look at this, all these relations, and tell me.
Ma'am, by substituting the partition function z
Okay. So if
zvn,
so, this is ZTVN, right? So what is ZTV1?
is it n equal
Putting n equal to 1, right? So if you put n equal to 1, what you get is ZTVN. That is the partition function, canonical partition function for one particle. Okay. That will give you this term here. Now how will you get this? You'll have to just use this relation, right? Is this clear?
yes ma'am?
Right. So that means this is your ZTV1, and then you put this thing here, you get ZTV mu. Correct. And once you find Z, you can find phi and the macrocanonical potential and the other thermodynamic parameters from there. Correct. Is this clear? Clear to everyone?
So, ma'am, the final equation that we get, that is the that equation would be for the macro, oh sorry, the grand canonical ensemble partition function, right?
Yes. This is how you are defining the macrocanonical or the grand canonical partition function. You knew the expression for ZTVN. This is something we had done in the last class. Okay, this is for a canonical ensemble with n particles. So now you can just, from here you can find what is the expression for one particle just by putting n equal to 1 here. If you do that, that will give you Z of TV1. And then you can use this relation to get to the macrocanonical partition function. Correct?
Yes, ma'am, understood.
Yeah, right. So now if you consider n harmonic oscillators, and we had done this solution in the last class. So this is your expression for the partition function for n harmonic oscillators, right? So what you have to do in order to write the partition function for macrocanonical ensemble? What will be the expression for macrocanonical partition function? Use this relation. You know this. So what will be Z of TV1? It's quite simple, right? Just use the relation. Yeah, tell me.
T divided by h cross omega.
KT by h cut omega, right? You're just putting n equal to 1 here. So that gives you Z of TV1. And then you just use this relation. That will give you the macrocanonical partition function. That's something like this. So here I have just written h cut as h by 2 pi. What is important is that So whenever you are dividing by n factorial here, you are considering that they are indistinguishable. But here, because it's a harmonic oscillator and we are considering that, so they are fixed in space and you can actually differentiate them. So that means here we don't have that 1 by n factorial, as you can see. So this is for a distinguishable system. Okay. So for distinguishable system, z of tvn is equal to z of tv1 to the power n. Right? So you just write n equal to 1, you get it for one particle and use this relation to find the macrocanonical partition function. Clear till here, everyone?
Yes, ma'am.
Yeah. Okay. Now, so that was about grand canonical ensemble. And so what's the main message is, if you can solve for canonical ensemble, you can solve for grand canonical ensemble. Okay, you just have to use the fugacity e to the power mu by kt term there, and then accordingly you can find the grand canonical partition function and find the macrocanonical potential and the thermodynamic parameters. So everything goes same. What I'll now discuss is this Ising model. So it's a very important model which is used to describe collection of atomic spins. Okay. So if you have a collection of atomic spins, and then if you give them a magnetic field, what happens is the spin tries to align in the direction of the magnetic field. And we know that it's given by something like mu h into Si, if Si are the individual Z components of the spin, considering that H is along Z. Okay, so that is already known to us. So spins try to align and they have different energy levels depending on whether they are aligning parallel or anti-parallel to the fields. Right. But now the thing is that if they are ferromagnetic, suppose, that means there is an inherent tendency of the spins to align with each other. Okay, that means if one spin is spin up, it's energetically preferable if the spins in the neighborhood are also spin up, or if one spin is spin down, it's preferable that the others in the neighbor are also spin down. Okay, there is this kind of a interaction between the spins that gives you this additional term. Okay, so this is called the exchange energy. For ferromagnetic systems, Z is greater than 0. That means, so now if Si and Sj both are plus 1, what happens is your energy is reduced. That means it's energetically more favorable, right? But if it was a antiferromagnetic, in that case Z would be less than 0. So what we are now talking about is the case where Z is greater than 0. So that means the spins try to align in the direction of in similar directions, and that reduces the energy. Now typically this exchange energy is electrostatic in nature and they have a very short range. Okay, so it's realistic to consider only like immediate neighbor interactions. So that means if you have a line of spins, it will interact with the one to the right to it and to the left. Okay, not the ones afterwards, only the immediate neighbors. So that gives you this kind of a pairwise SISJ term. So now if you know that, so what you can do, the first attempt that someone can do is to do a simplification of the mean field approximation. Okay, this is called mean field for a reason. We'll see what. So if you look at the total energy here, what would be the energy for the ith atom? So what you can then do is you will consider one ith atom. So now the ith atom will get a, if it has z nearest neighbors, it will interact with z such neighbors. So you'll have k which So the summation goes from 1 to z. Okay, and then you're dividing it by g by 2 because you want to ensure that you don't like count the pairs twice. So for ith atom, this is your interaction term, and this is your term which comes from, this is the normal term that we get because of the spin trying to aligning with the incident field. Okay, so this is the energy for the ith term. Now what one can do is one can write the expression for this energy EI for the ith atom or ith spin by this relation here, where H is replaced by H effective. Okay, so this is the effective magnetic field, which is made up of two components. One is the external applied field and one is the internal field generated by neighboring atoms. What we then do is, now what is this expression telling you? That means now you have a single atom in some magnetic field HM. So for our case, later we'll see that HM is equal to H effective. So we know that when we have a single atom in some magnetic field HM, this is how we write the mean spin, right? The one that we have in the below is the partition function. We multiply each, so e to the power beta mu by mu HM by the partition function is the probability of being in spin minus 1. This is the probability e to the power minus mu beta mu HM by Z is the probability of being in the spin plus 1. And so what you do is you multiply the probability of being in plus 1 with 1 and probability of being in minus 1 with minus 1, and then you add them to get the mean spin. And this is the mean spin of the atom. This is known to us. This is how we have been solving for the different canonical ensemble questions, right? So that tells you that the average or the mean spin is given by this expression here. Now, if you go back to this question, what this tells us is that now you can effectively consider the system to have a mean spin of S bar and experiencing an effective magnetic field of H effective. Okay, so that means you can replace HM by H effective and replace this SK term by the mean spin. So if you do that, you get this expression for H effective, and this is the expression for the mean spin. Okay, so what is then done here is that they are defining some critical temperature and critical magnetic field, and we'll see why it's useful. Is that, see, this expression can be numerically, it can be solved, and then you can get to this expression where it has all this TCHC terms which are uh, which are given by the expressions here. So now once you know the mean spin, you can find the magnetization, which is given by this expression here, right? So now magnetization is what is relevant to us, because if you have a substance or if you have a system of some number of spins, what's interesting to find is this magnetization. That tells us whether so how does the system respond to some field, or it defines its material properties as well, right? So this is our system of the parameter of interest. We want to find this, and once we find S, we can find M. What this tells us is that now with this mean field approximation or mean spin approximation, we get that at b equal to 0, we get a graph like this, and for b not equal to 0, we get something like this. What this tells us is that for b equal to 0, there is a particular value of temperature, okay, below which we have a net magnetization, beyond which there is no net magnetization. Okay, so there is some kind of a phase transition that is going on. And what we get from the case when b is not equal to 0 is that now there is no such transition if we look at how like if you look by changing temperature. But if you consider a fixed temperature, you see that depending on the value of the incident field, your magnetization changes from negative to positive value. Okay, so there is some kind of a phase transition here as well, where if we keep the temperature fixed and vary B, magnetization changes from plus to minus. So all this what we get tells us about some phase transitions, and this happens when we consider the mean field uh, mean field approximation. But the problem with mean field is that we assume that all atoms are situated in identical environments. So all of the atoms have a mean spin and they are seeing the same field, same H effective. But that is not always true. Okay, so this approximation that we are doing is not justified in all cases. That is justified only in the cases where we have a, a huge number of where the dimension is quite high. But suppose in one dimension or the case that we are doing here, you'll see that the mean field model fails. Okay, so this transition that we are seeing is not correct, and we'll see that if we solve this thing exactly, we'll see that there is no transition that is happening. Okay, so this is the exact solution. Okay, and what this tells us is that this is the same Hamilton that we had started with, but now we had written it in terms of immediate neighbors. Okay, and we have distributed the so we are considering this is si plus 1, so it's the interaction with the immediate neighbors, and then we have divided this interaction with the magnetic field by this term here, where we again, so this is to make it symmetric. Okay, so if what we do here is, now we don't do any approximation, we solve it exactly. Okay, we do a summation over all the possible values of the given n number of spins, and what this tells us is that we can write Z in terms of a matrix. Okay, so each of the terms can be written in form of a matrix like the one given here, considering that both Si and Si plus 1 can vary from plus 1 to plus 1 and minus 1. So that gives you this transfer matrix, which shows how one spin interacts with another neighboring spin. And then you have n number of such spins. So what you do is a total stress. Okay, so that gives you the effective partition function, the total partition function for n number of spins. What you can then do is that you can solve for this matrix, find the eigenvalues of this matrix, and that is how one spin interacts with another spin. And then you have such n number of pairs, so that means you can multiply it by, so each of the terms can be raised to a power n. What's interesting is one eigenvalue is less than the other, so you can do this approximation. So that gives you the effective partition function as z plus to the power n. Okay, so this is the exact solution, and what this tells us is that now if you use that expression for Z and find the magnetization, you'll see that for D equal to 1, M is 0, which is different from what we had got from the mean field approximation. So when B is 0, there is no magnetization for one-dimensional case. And this is a general lesson for all this kind of systems where you have n such particles and they're interacting, and whether you'll get some ordering or not, which tells us that thermal fluctuations always win in one dimensions. Okay, so mean field approximation is bad in one dimension. It will hold better in higher dimensions where you will have more number of neighbors, and then each spin can effectively be approximated with a mean spin. Now, all this that I was talking about is to explain to you the Ising model that describes such kind of magnetic systems, ferromagnetic or antiferromagnetic. And so while they have physical, like they have huge significance in describing physical phenomena. Okay, and so this is for 1D, you can do it for 2D. as well. So you can get exact solution for 2D as well for b equal to 0, and you can see some kind of a phase transition. Now, what I'll now do, why I was talking about Ising model, is that this is a very important concept that people should know, like everyone should know, and it's also relevant for in cases of solving questions, because in all competitive exams or wherever it may be, you will get some questions based on this Ising models. Okay, so the concepts, so whatever I was discussing was the physical interpretation of the system, and then the concepts that we use for problem solving is similar to what we use for the other questions, like the ones for solving the ensemble problems that we were doing. Okay, so you'll see it's not very different. So now suppose you have this question. Okay, you have this one dimensional Ising model with n spins at very low temperature, while almost all spins are aligned to each other. Okay, and then there are some spin flips which costs an energy of 2J, where J is your exchange energy. Now in this configuration, so suppose if you consider that you have R spin flips, what will be the energy of the system? It will be given by the expression given here. So you need to find the partition function for this system. So initially consider the case of just two spins and think how they can interact with each other and what are the different energy levels, and then you can extend the case for n spins. Try to solve it and then I'll discuss the solution. Is the question clear? Think of two spins and think how they're interacting and what would be the different energy levels that's possible when there's a flip. Are you guys thinking, or should I share the solution? So let me share the solution. Maybe it would be helpful for you at the first place, and the next questions you can try. Okay. So let us consider two spins. Okay. Now if they interchange, yeah, tell me. Okay. So if you have two spins, what can happen is you can have the energy levels ranging from minus 2J, 0 or plus 2J, depending on whether they're both aligned in the same direction, like both spin up or both spin down, or like one spin up, one spin down. There are two configurations of the case where one is spin up and one is spin down, right? And there are each one cases of being to spin up or being to spin down. So that means what you can do is, this is your partition function, if you just consider these two spins. So when the energy level is minus 2J, the probability is 1 by 4. So out of the 4 states, both up, both down, 1 up, 1 down, 1 up, 1 down. Out of this 4, there is 1 by 4th chance of being in both spin up. There is 1 by 4th chance of being in both spin down. And then there are 2 ways. So that means half chance of being in one spin up, one spin down. So if you do that, this is the expression for the partition function of 2 spins. Now if you have n spins, what you can do is you can change or replace this 2 by n, because now you'll have your energy levels will vary from minus n j to plus nj. Okay, so then you'll get an expression like this. So in this case, your answer will be D. Is this clear?
Yes, ma'am.
Okay. Question. You have a system with two Ising spins. They can take values plus minus 1, and this is your interaction energy. Now for large T, what is the average energy of the system? This you should be able to do. Consider, first find out that if you have two spins, what are the different energy levels? What is the degeneracy, or what are the number of microstates possible corresponding to that energy level? Okay, what are the how many number of spin configurations can give you the different energy values, and then find the average energy. So here you have to use the concept that it's for large T. That means you have to expand. So you'll get some exponential, and then you have to expand it. So try to solve this. You should be able to do it by now. So what happens when both S1 and S2 is spin up? What is the energy level? And then what is the energy level when both are spin down? What is the energy level when one is spin up, one is spin down? And what are the different ways in which you can get these combinations? Find that first. So that will help you to get the partition function.
Ma'am, is it the partition function for cos h, cos hyperbolic of beta j?
So don't write it in terms of cos hyperbolic, because you have to expand the exponentials, right? You have to use this relation of being in large T. So you'll get some 1 by kt term, right? So for large T, that value will be less. So you can expand e to the power that term as 1 plus x, right? Do that expansion, otherwise you won't get the answer. So once you get the partition function, you have to use, you have to find the average energy. So average energy means multiplying each energy value with the probability of being in that energy state. Should I share the solution? Or you guys try?
So the solution, ma'am.
So see, what are the possible values of energy? So one can be both spin up, okay? That gives you an energy of minus J. Another is both spin down, that gives you an energy of minus J. And then you can have one spin up, one spin down, and that gives you again plus J, right? So that means there are two ways in which you can get minus J. There are two ways in which you can get plus J, right? So now if you find the average energy, you're multiplying each energy value with the probability of being in that energy state, right? This is your Z, and Pi by Z is like e to the power minus beta Ei by Z is Pi, probability of being in the energy state Ei, right? And then you multiply by the energy and do a summation to get the average energy. So if you do that, you get an expression like this, okay? So this is your, I forgot the expansion for sine by cos. Yeah, it should be, uh, this is sine hyperbolic, this is cos. So from here you get an expression for cos hyperbolic, right? But but that is not required here. What you can now do is you can do an expansion. E to the power j by kt can be written as 1 plus j by kt, and then similarly the other terms. And then if you do that, you get the average expression for energy as something like this, right? So your C value here is given as minus J square. Is the solution clear?
Yes, ma'am.
Kamalesh, it's matching.
Yes, ma'am.
Okay. Now this is another question. Here you have three spins and each of them can take values plus 1 and minus 1. You have to find the minimum energy and the corresponding number of spin configurations. So what is the minimum energy? So this you can just solve by looking at the question. So you have a minus J in front. That means the energy will be minimum when this term will have the maximum positive value. So what is the maximum positive value of this term?
Ma'am, when the
Yes,
All
tell
the
me.
the all the terms in the bracket equals 3.
Like 1 plus 1 plus 1.
Yes, ma'am.
Right. Because that means all of them are pointing in the up direction. So 1 into 1 plus 1 into 1 plus 1 into 1. That's the maximum positive value. That means that's the minimum energy state. So that should be minus 3J. Right? So these are the two options now. Now, how many ways is that possible?
Only one.
Is it so? They are in the same state. See, 1 into 1 is also 1. Minus 1 into minus 1 is also 1.
So all are up and all are down. That means two.
Correct. So the answer should be C. Right? Clear? And then if you have one spin down somewhere, you will get a energy of J, and that's the maximum energy. Okay. So in this case, the answer should be C. Clear? Okay. So now this is another question. Here you have three Ising spins at three vertices of the triangle, and then you know that the interaction strength is J, and then you have to find the partition function of the system. So you have to find the different possible energy levels, and in how many ways is that energy level possible. Because partition function is the summation over all values of e to the power minus beta ei. Beta ei, yes, correct.
D, ma'am.
Hmm?
Option D.
Try to solve, just don't look at it and tell. What are the different energy states? First tell me that. You have three Ising spins, plus 1 and minus 1. What are the different energy states possible? Make a table S1, S2, S3 and see, like, if you put all 1 and all minus 1 and all possible values, all possible combinations of plus 1 and minus 1, what are the different values of energy term that you are getting? The energy expression of the Hamilton, you know what would be the Hamilton, right? Hamilton will be J into S1 S2 plus S2 S3 plus S3 S1. It's similar to this question. There also you had three spins. Here also you have three spins. So this is your Hamilton. So think of the different values of S1, S2, S3 and the different energy states possible.
Ma'am, please show the previous expression. Yeah.
See, you don't have to remember this. You have to understand that the interaction strength is J. You have three spins. So one can interact with two, okay? Two can interact with three, and then three can also interact with one. So these are the three possible pairs that are possible, right? S1, S2, S2, S3, and S3, S1. Correct? Think of how many ways you can pair them. S1, S2, S2, S3, S3, S1. and this is your interaction strength.
I am getting option B for the just only the two.
Okay, so how are you getting option B?
We have a two combination with e to the power minus 3j
Hmm.
and all other combination uh, giving the plus e to the power plus j. So plus 3j.
So now e to the
So
power
two
minus.
yeah just so in partition function we have just two factor 2 e to the power minus 3j. So we just add the e to the power minus 3j plus e to the power minus 3j, and if we arrange up and down, get positive value.
So everything is fine, but the expression is e to the power minus beta e, right?
Yeah, yes.
So minus of minus 3j. You're getting something like this, correct? You are you getting something like this? So here the
Yes, yes.
sign convention is slightly different from the last question. See here it was minus j. So here in this case it should have been minus, but
Oh, yeah, sorry, ma'am. I said you just to the power minus j. Oh,
yeah, it should be minus j according to the idea that when they align, they try to reduce their energy. So it
but
should have,
positive value, uh, the answer is different now.
yeah, the answer here is B, but they have considered this Hamilton. What I think
Yes,
is also possible is to consider the Hamilton of minus j s1, s2, s2, s3, s. Okay, so in that case, the answer will be this.
yes, yes. So
Be-
what is the right answer? Because
So I
from
guess,
this
see, I guess because they have mentioned the strength as j, that's why
yes,
this is how you have written the Hamilton. But if you would have just told about three spins, you can always consider this expression because see j, if j is positive, this is how your Hamilton should be, because this tells you that when they align, your energy is less. For ferromagnetic system, the system always tries to align in the same direction because that is energetically favorable. So in this case, when they are aligning, you have more energy, right? But physically, it would be preferable to have all this aligned. So it's more physical to consider the Hamilton as minus j s1 s2 s1 s3 s2 s3. Okay, but because the
and
question,
you
yeah,
had also found that the strength of the energy is in general minus j si as j in terms of Ising model.
correct,
Just we have
because in ferromagnetic system the spins always preferably try to align in the same direction. That is always energetically favorable. So if you consider that
okay.
physical argument, it should have been minus j. What I think, because the question already specifies explicitly that it is j, so they have considered it to be j. Okay. So because it's
So
explicitly specified, they have taken it as j. Otherwise, you should always take it as minus j.
according to the question, answer will be A. Na?
According to the question, the answer will be B because the strength is specified as j. Okay. This is another question. You have this Hamilton, and then you have to find the average energy of the system. Try to find the different energy levels considering the different values of S0, S1 and S2. Are you guys trying?
Yes, yes, ma'am. I'm trying.
Did you find the different energy levels?
Yes, I am getting answer D.
D. Okay.
Yes.
Okay. So let us see what's the solution. So these are the different values of S0, S1 and S2 and the different energy values. Okay. So that means there are four ways of getting zero energy, two ways of getting -2 and two ways of getting +2J. Okay. So now if you find the expression for U, this is how you'll write the expression, and then if you solve it, you get to the expression here, right? Yes, it's answer D. Kamalesh, is it clear to you?
Yes, ma'am.
Right. Okay. So I guess that was all. So next day, I think it will start with the quantum statistical mechanics. So the description of density matrix and all of that. So that's all for today. Do you guys have any doubt regarding anything that we had discussed today?
Ma'am,
Yes. Hello.
can you hear me, ma'am?
Yes, yes, tell me.
Ma'am, the recording of the session is available.
Yeah, the
to-
recording of the session will be there. So I'll there's a sheet, right, where you get the link to the YouTube link and the PDF of the slides and everything. There's a public sheet that is supposed to be shared with you people.
We will check.
Yeah. Okay.
Ma'am, can you explain again the connection between canonical to macrocanonical and symbols? The expression
Yeah.
for the macrocanonical.
Yeah. So see here, if you start from here, you find this is your expression for entropy, and then this is how you define average energy, average number of particles. If you put that expressions, like if you compare with the expression for entropy, you get this relation. Okay. And there what you can do is, that means this z, okay, you can just directly look at the expression for z. So if you look at the expression for z, this is your expression, right? Minus beta h. So if you consider just canonical, it would be just e to the power minus beta h. But now it's macro canonical, so you have this additional e to the power alpha n term. Well, alpha is mu by kt, mu is the chemical potential. Okay, so this thing can also be written by the expression given here, right? So here, this is for continuous energy level, like continuous system. This is for a discrete system. So in discrete system, you would have a summation over n, and then you would have e to the power mu by kt, which is this term, in to the power alpha, because e to the power alpha n can also be written as e to the power alpha to the power n, right? So this is this term, and then you have z of tvn, which is the canonical ensemble for n particles, right? Is this clear?
Yeah.
So
Yeah.
yeah. So now if you have indistinguishable non-interacting particles, you can write z of tvn as z of tv1 to the power n by n factorial. If it was distinguishable, you wouldn't have had this 1 by n factorial. It will be just z to the power n. Okay. So that means whatever expression you get for the canonical ensemble of n particles, you can use this relation to find the canonical ensemble for one particle. Okay. And if you if you put this relation here, what do you get? N to the summation of n equal to 0 to infinity e to the power mu by kt into z of tv1 to the power n by n factorial, right? So that this expansion, like this summation of anything to the power n by n factorial, is actually the expansion of a exponential function. So this summation can also be written as exponential of whatever you have here within this third bracket, right? So if you have the canonical ensemble, you can write the canonical ensemble for one particle, and then you can write the canonical macro canonical ensemble using this relation. Otherwise, if you have the canonical ensemble for n particles, you can directly use this relation to find the macro canonical and canonical function, macro canonical partition function. Is this clear?
Yeah, yes, ma'am.
So this is what we have done here, where uh, for ideal gas, you get the canonical function for one part for n particles. You find the canonical partition for one particle, and then you put it in the formula. So this gives you the macro canonical partition function. Okay. Anything else? Okay. So if not,
Ma'am,
yeah.
actually, I need this slide instantly. How I get? Because I can't wait for 2 3 days for updating on the web page for this slide.
For which slide?
Is current slide today's slide?
So if it is only this slide, you can just click a picture and keep it. But do you need
No,
the
no, no, no.
entire?
No, no, no. Just all slide, not a particular, but today's all slide. Yeah.
Okay. So how am I supposed to do that?
Because they update in the last of the week, I think.
Okay. Um, I don't know what. Okay, wait. Let me first. Second, let me stop the recording first. Okay.